So this is the last video that I made an audio for in a different file. So this is an RLC in Laplace, and we're going to start with the initial conditions here. That would have been the first step. Usually it's going to take much longer to solve a circuit like this. We're already going to go to the second step, which is to draw the same circuit in the S domain. So the 5 Henrys and the 0.1 farad capacitor will be drawn with their own initial conditions, which are the current's -1 amp and the voltage across the capacitor is 5 volts. So let's get started with that. So I'm going to draw the 10 U of t is 10 over S. That means at t equals 0, that power supply starts at 10 volts. And then I'm going to draw in series with the inductor a current supply. And I'm going to assume that the current through the inductor is going down as well as that current supply. So 10/3 ohms. And then the capacitor will be in series with a voltage supply with a plus on the top side. That's going to be 5 volts, 5 over S. And then 1 over SC, because it's 0.1, I'm going to write 10 over S. This current supply here, if you see there -1 amp, I'm going to write that -1. It's -1 over S. So this minus here is just because of that minus on the initial condition. And then the polarity on the inductor, I'm choosing because I'm assuming the current on that inductor, the 5S inductor, is going down. So now I'm going to do nodal analysis, and here if I find V1, I can use that as the voltage across the capacitor. So let's write this for nodal. So I'm going to say the current on the 10 over 3 ohms is going in. Everything else, all the other currents are going out of that node. So I'm going to get started with that first one. And using Ohm's law there, it's going to be 10 over S minus V1 divided by 10/3. Let's take a look. And that's going to be then equal to V1 over 5S, which is the current through the inductor, minus 1 over S, which is the current on the initial condition on that inductor. And then it's the current only through that capacitor, which I'm going to call V1 minus 5 over S divided by 10 over S. So this is a one variable, V1, oopsie, not equal 0, huh? Yeah, my mistake there. So this is a one variable equation, and we can just isolate V1. So it does require, a couple minutes of putting this side or the other side. So I'm going to just write what I got for this one. And if you guys find anything different, please let me know. But I found this V1 equals 40 plus 5S divided by S plus 1 times S plus 2. I'm not claiming it's completely right. I think actually I lose a lot of points on these algebraic manipulations. And then we're going to do partial fraction expansion PFEs to find A and B, just like Alvin posted last week on his video for Monday for 420 class. And we're going to try to find A and B, and this is a simple, we can use the residue method to find both A and B. So I found, again, it may be wrong, but I found A equals 35 and B equals minus 30. And so I can rewrite V1 as 35 over S plus 1 minus 30 over S plus 2. Now I have a feeling this is right, and I hope you guys do take a look at this when you are doing these problems, that because the voltage across the capacitor at t equals 0 is supposed to be 5 volts. So 35 minus 30 is 5, so I'm confident that these two numbers are good, or it would have been 40 minus 35, for example. So now I'm going to do the inverse transform, of course, which is 35 e to the minus t minus 30 e to the minus 2t, and this is only valid for t larger than 0. Here I'm explaining how I should check that that is, this complies with the initial condition on the capacitor. So here you see how this does make sense. This is different than what we did in 285 because we don't need to go back to add initial conditions. So basically, this V of t is the complete solution to the RLC circuit, which is the forced solution plus the natural solution. So from the beginning of the circuit, that 10 volts is what's forcing the circuit to, the voltage to go to this 35 e to the minus t minus 30 to the minus 2t, and the current on the inductor and the voltage on the capacitor, both the initial conditions that we're complying with. We're assuming they are all in there. I also hope that this is not as hard as used to be in 285 to solve differential equations, to solve RLC circuits, and now you can solve any kind